I got an hour's worth of talk to do, or 45 minutes, but you guys are terrifically lucky to have him here. I cannot tell you what a steal you've done, and what a hole he's left at Case. And I was telling him this morning that I'm trying to fill in those pebble by pebble, but it's going to take a long time. Yeah, this is all new. It's based upon many, many years. I turned 62 in June. Many, many years of frustration, kicking things around. This solution that you're going to see today literally came to me when I was getting out of bed one morning. You work with a problem long enough, and sometimes it'll happen. So there was that aha experience. And I've put it together in a fairly jazzy talk, as you'll see. And I've got some money up here. These are uncirculated dollar coins. It's a trademark of mine. I've got 2 here, and I've got a roll of uncirculated ones that I'm willing to break for good questions and good comments. So I do pay. My wife was not all that happy when 500 of these arrived in the mail one day from the U.S. Mint. And she said, "What are these?" And I said, "Well, I give them away when I teach and stuff." And she goes, "You do what?" And then I had to tell her that for years I've been going to the bank at $20 a time and getting 20 of these and doing it. But it works. It works very effectively. So you can be bought. All right? And I appreciate it. So this is all about a discussion between 2 characters. You've already met Maxine, stat scientist. Obviously, she's my alter ego. And today she's going to work with a clinical investigator named Will Treatwright, MD, Ph.D. And Will today he's an expert in tropical diseases. And so we can couch everything that I'm going to do in terms of the conversation between these 2 people. It frees me from being as preachy as I usually am. Now I can preach through Maxine. So Will says, I heard you're developing a new schema that takes your March of Science notion for sample size analysis and extends it to data analysis. And Maxine says, yeah, that's correct. I'm quite excited about it. Are you ready to show it to others? Yeah, but I only have about 45 minutes today. All I can do is show examples. I don't have time to give the mathematical basis to show you the evidence that it really works. And then Will Treatwright, MD, PhD, comes back and says, perfect. When statisticians enter math land, they lose me. Yeah, great. This gives me another opportunity to ensure that what I do is useful and understandable to researchers. And so what I'm going to say is what I do in these talks and everything that I do, collaborating and consulting is my laboratory. It's where I get my ideas. It's where I test them out. It's why I like to come down here, especially in March. If you saw the weather in Cleveland today, and I get to stay with my best friends in the very whole world from graduate school and all that kind of stuff. But this is my laboratory. So whatever comments you have, I take back and things get worked out. All right? So Maxine says, I'll use your study on Furlingia as an example. Now, I'm not going to tell you where Furlingia comes from because I have all kinds of things that remind me of things that happened in the past. But I will tell you where Furlingia comes from. Furlingia is a derivative of a Dr. Furling that I had as an undergraduate. And let's just say I didn't like him. And neither did any of the other students in the math department at Claremont McKenna College. And so I've now named a disease after him. So be careful. Be careful, okay? So please summarize it, says Maxine. So now we're going to summarize Furlingia. This is all about a statistical fable. I can work in all the teaching principles I need through a fable. It works very effectively for me these days. So Will says, I'm investigating whether or not a new treatment can reduce mortality rates in young children infected with a tropical disease called Furlingia. Now what I want to tell you is this is just a pseudonym for malaria. Okay, so this is very similar to malaria. Furlingia is a tropical disease that infects mostly young children during the rainy season. Its incidence rate, about 3%, will contract severe Furlingia before reaching age 5. Usual care is hospitalization to treat high fever and dehydration. And mortality rate for Furlingia, for severe Furlingia, is about 40%. So 3% of the kids will get it, 40% of those 3% will die. This is true of malaria. If you don't know, it kills about 1 million kids a year in sub-Saharan Africa. It's like flying a Boeing 747 into Mount Kilimanjaro, 7 Boeing 747s into Mount Kilimanjaro every day. It's still a disease that racks us. But this is for Lingia, okay? Experimental therapy is BIOS 266. The last time I gave this talk was down in Chapel Hill, and I gave it to Roe Incorporated. Roe Incorporated was founded by Ron Helms. Ron Helms was the best stat professor I had ever, and Biostat 266 was the linear models course that I've told you about 1,000 times, Sunil, and what set me straight in terms of modeling and all that kind of stuff. So I named the course, I named the therapy after the course that Ron taught. Mortality, defined as death within 30 days. So we got a very simple endpoint here. This is not a survival analysis. This is just whether or not they make it to 30 days. Keeps everything simple. Dropout rates are less than 3%, and now we get to say non-informative. I get to make up the fable, so now I don't have any problems, right? Don't have to deal with and bad missing values. So here's a design. We're going to take a sample size of cap n, divide it into two pieces, little n1, little n2. We're going to randomize, all right, put n1 over there into BIOS 266 and n2 into usual care. 30 days later, we're simply going to ask, did the kid live or die? Anybody have a problem with this design? It's about the simplest design I can come up with, and yet I can teach everything that I need to teach in here with this very simple design. So here's a new slide in here, a traditional hypothesis testing schema. I like to give this same talk to statisticians, even at the joint stat meetings. I give a similar talk. I'd give it probably in front of a group of transplant surgeons if they wanted to. So a little review here of what the traditional hypothesis testing scheme would be here. We've got a continuum mortality difference, Biostat 266 versus usual care. We would measure that. So we measure the kids that, what percentage of kids die under Biostat 266, what percentage of kids die under usual care. We set 0 as what I'm going to call today an exact null, all right, otherwise known as a point null, but today we're going to call it an exact null, and you'll see a little bit why. And we've got data. We've got superior over there on the left-hand side, the superior range. We've got the inferior range over on the right-hand side. We're going to have some distribution now. You've seen this in every stat textbook. We're going to mark off some region over there at the 025. We're going to put another region over there at the 025. And let's suppose we got a result there on some t-test or whatever, result over there at, well, looks about 0.01, let's say. All right? And so that would be the 0.01. And we'd multiply that by 2 for reasons that we'll get into and I've never understood, okay? We'll multiply that by 2 and we'll get a p-value of 0.02, all right? And so where is Maxine coming from? Where is Maxine coming from today? Why did I start working on this problem, all right? Well, Maxine Chance believes, all right, that the usual two-sided hypothesis schema rarely makes any scientific sense, all right? So she's saying, why do we usually double the p-value? This lumps two completely different hypotheses, say, Biostat 266 works superior, BIOS 266 is inferior, into a single alternative hypothesis. And she's saying it's never made sense to her. All right? So here's what she's saying. Well, we got this result over here, and it's superior, and it's a 0.02. But we got this result over here, and it's inferior, and it's a 0.02. Oh, but it's the same as this one over here, and it's the same as this one over here. And you know, I really don't understand what's going on here because you're treating these things as the same because we lump them all together. We say, oh, it's just not null. All right? So we've rejected the null hypothesis without regard to direction. So she says that's a problem. All right? She didn't like that. Dr. Chance also believes the common point null hypothesis is almost always implausible. Almost always implausible. So she says, why would anybody think that BIOS 266 and usual care have exactly the same mortality rates? Exactly, to the 20th decimal place, if you will. Why would anybody believe that any two groups have exactly the same on anything? Exactly the same. We need to be asking how much of a difference is there, all right? And that's why in my teaching I stress confidence intervals, confidence intervals, confidence intervals, which those of you who've studied both frequentist and Bayesian know that the frequentist confidence interval is frequently pretty close to what the Bayesians would do, okay? With the, with pretty flat priors and those kinds of things. But let's concentrate on the difference. So here's our graph again.